Okay, so here we have a Newton's laws problem involving systems of objects, and those can sometimes be complicated because there's a lot to keep track of. So you have to work through them very slowly, which is what I'm going to do here. And I've also kind of color-coded it just for simplicity. So anything that deals with block M1, that's in green as it shows there. Block M2 will be in blue, and the hanging mass, capital M, will be in red. So hopefully that'll keep things a little clear as well. So part A, I find tends to trip students up because they go through it too quickly and not carefully enough. So you have to do two things in part A for each of these 5 different questions. And that's figure out the direction of the force and determine the magnitude of the force. So if there is no direction, you don't, right, if it's 0 magnitude, then you don't draw the direction and just write that the magnitude is 0. Otherwise you draw an arrow and then calculate or show somehow. And most of these are very, very fast, right? This is really walking you through, in some sense, the first step to any problem, which is make a free body diagram for every object. But instead of doing every single force all at once, you're doing sort of individual forces bit by bit, and you're also not doing exactly every force. But that's all it really is. You should be thinking about it that way. And we're told that everything is at rest, which is a very important statement, right? If the blocks are moving, then the acceleration from F equals ma will change some of these forces. So they're all at rest. The net force is 0 on each of the blocks. So first, question 1 is the normal force N1. I see that I've done the color wrong here. We want the normal force exerted on block 1 by block 2. So it's always critically important, right, to make sure you're knowing what thing exerts the force and what thing feels it, which is why I changed that color pretty quickly. So block 1 feels a force that pushes upward from block 2, right? Normal force is just a contact force that stops things from falling through other things. So that must be, actually that's N1, right? That must be it. That's the force that stops block 1 from falling down. We know since it's not accelerating up or down at all, and block M1 has weight M1g, N1 must exactly balance that. So when I did the calculation, such as it is, it's really just N1 equals M1g. That's it. Right? All I'm saying is the normal force balances the weight. Very straightforward. Question 2, friction force. The friction force exerted on block 1 by block 2. Well, this is going to be a horizontal force. So we have to think, what horizontal forces could there be? Right? Friction forces prevent or oppose motion. It's not moving. Right? Block 1 is not moving. There's also no other horizontal forces, right? If I was going to do a free body diagram for block 1, it would have the normal force, the weight, and then potentially this friction force. That would mean there's only one horizontal force. If there's only one horizontal force, the net horizontal force cannot be 0, and therefore the block must be accelerating left or right, which it's not doing. So the only conclusion we have is when the blocks are all at rest like this, the friction force on block 1 must be 0. Because if it wasn't 0, the block would have to be accelerating. There's no other horizontal force to oppose it. This is probably the single most common mistake I've seen with this problem, right? Is doing the calculation is mu times n. Well, remember, it's a static friction force, right, because it's not moving. And since since the static friction force is variable, it can be 0 if it doesn't have anything to oppose, which is what this case is. All right. Question 3, now we're moving to block 2. And so it's pretty easy to get the direction of the tension, right? The direction of the tension is always in the direction of the string. So that's easy. The magnitude, though, is potentially a little bit trickier. You kind of need to think about, well, what's causing the tension? What's causing the tension is that thing, right? If I drew a free body diagram for that hanging mass, which I'm not required to do, but if I did, it would look like that. And since A equals 0, we know that the tension equals capital Mg on that block. But since the string is lightweight, that means the tension's the same everywhere in it. So the tension must equal capital Mg, right? Because it's calculated sort of from the other block. All right, question 4. Normal force N2 exerted on block 2 by the tabletop. So So first of all, again, it's very obvious that it's up, right? The normal force prevents things from falling through other things. The tabletop prevents it from falling down, so it must be exerted upward. Getting the magnitude is a little bit tricky. Your first instinct might be to say, well, just like this one, so if N1 is M1G, N2 must be M2G. But that's not right. Because if I was going to draw a free body diagram for this block sort of in full, we have to remember Newton's third law, right? If N1 here points up from block 2 on block 1, there's an N1 down from Newton's third law, right? And then we have N2, which is what we're trying to find, and we have the weight M2G. And we have the equation N2 equals N1 plus M1G, right? It has to balance both. And we know N1, so we can now quickly just write it. Right? In essence, the normal force of the table has to balance both weights, which I think is a fairly obvious statement, but if you forget that and just sort of work too mechanically through it, it's an easy mistake to leave out one of the masses there. And finally, the friction force F2 exerted on block 2 by the tabletop. So, similar reason to question 2, but now we have a tension, we have a horizontal force to oppose. So we know the direction, right? But remember, this is again static friction, and static friction is variable. All we know is that it's at rest. We don't know if it's sort of the maximum amount of weight that would be putting it at rest or what. All we know is that the friction force has to balance the tension perfectly. If it didn't, it wouldn't be at rest. So friction force 2 must balance the tension, and we know what the tension is. So it must be capital mg as well. I went through this very slowly. Some of these parts should be very quick, but you have to be very careful because free body diagrams, when you have systems objects, are tricky. So that's part 1, which is quite long. The other parts are now going to use some of those results and also make some changes and do some calculations. So the largest value of capital M for which the blocks can remain at rest. Well, anytime you see stuff about maxima when you have friction, means that we're calculating the maximum amount of friction. So the blocks remain at rest as long as, as long as the condition for block 2 is met that T equals F2 max, right? If the tension is bigger than that value, then the blocks will start to move. If it's anything less than that, then it'll stay at rest. But we can calculate a maximum value of static friction, right? Actually, it's US2, right? So that one we can calculate because it's a maximum, right? Static friction we can calculate the maximum for that way. And we know N2 from our previous work, right? And we also know the tension from our previous work, right? It's at rest, so that's still capital Mg. And now we can see that the g's will cancel on both sides, and we're already essentially done just from sort of substituting in the information that we knew. Capital M at most can be US2, it's kind of sloppy. Always trying to write too small on these. Right? Anything more than that will mean that the tension is bigger than the maximum static friction force, and it slides. So that's part B. So now we're changing some assumptions for part C. We're saying that the mass is large enough that the hanging mass will actually descend, and therefore block 2 will start sliding. But we are going to assume that blocks 1 and 2 move as a unit, right? Block 1 stays at rest relative to block 2. And so for this one, when I see something like that, if block 1 and block 2 move together, there's no reason to overcomplicate things by treating them like separate objects. Just combine them into one block, which I'm going to do in black. So the system that I'm really going to be considering here, actually I'm going to do it in the dark green, is going to be one block, which is mass M1 plus M2, and then the one hanging mass, capital M, right, like so. and then we accelerate down and accelerate to the right. Really, that's the system we care about here because they move as a unit. It doesn't matter where the string is attached, that is only touching block 2, because block 1 and block 2 move together. The string has to provide enough force to accelerate both masses. And this system is much simpler to deal with. So if I draw a free body diagram for this combined 1 and 2 mass, right, we have a tension here. It's moving, so I'm going to do kinetic friction. And since the thing that is sliding is between the tabletop and M2, the coefficient of friction is going to be mu K2, so I'm going to give this a subscript 2 to indicate that that's the surface that matters, block 2 in the tabletop. We have a normal force and a weight as well. I'm going to leave those temporarily not written. So the weight, since we've combined both masses, is just m1 plus m2g. And that tells us what the normal force must be as well, right? It's the combined normal force, or sorry, the combined weight that matters. Right, so now we know everything about that. Block 2 doesn't, or block capital M doesn't really change, right? However, it's important to note that the tension is not equal to capital Mg anymore because it's accelerating. So all we've done is the free body diagram. We haven't done the math yet. So now we want to write Newton's laws and solve the system, right? Because we have two things we don't know. We don't know the acceleration and we don't know the tension. We're only asked for the acceleration. So for the green block, the combined mass, we have the tension, that's the direction of motion, so it's positive, minus the friction force that opposes it, equals the combined mass, that's the total amount of stuff that's moving, times A. And for the hanging mass, capital Mg, because it's going downward, that's the positive one, minus T, equals capital Ma. And so we can see that we have two unknowns, but two equations. So we can solve. We just have to do some careful algebra. So the first thing I'm going to do is solve this one for tension and plug in solve the green one, right? Solve that for the tension and plug in what we know the frictional force to be. So T equals m1 plus m2a. So now plus the friction force, which is mu k2, and that should be times n2, but we know what n2 is right there, right? It's m1 plus m2g. And then this whole thing will go right in there, and then we'll have a single equation to solve, which I'm going to transfer to use black for, because now we're sort of not dealing with individual objects. I'm also going to do it on the next page. So I'm just going to substitute that in and write the result. So we still have the capital Mg, that doesn't change, and then we subtract the whole mess of other stuff. Oh, actually, yeah, okay, so I wrote everything right, yeah. So we subtract this, mu k2 m1 plus m2g, and then we have to add on the m1 plus m2a, that's all there. And that whole thing equals still capital Ma. So I've just substituted in what we know the tension to be. All right, double checking to make sure I got the signs right, which looks good. Okay, so now we have only one unknown, right, A. So we just need to put everything with A on one side and clean it up a bit. So Mg minus mu K2 M1 plus M2G equals A, and we'll factor out all the other stuff, so that capital M. Now, this M1 plus M2 comes with a minus, so I have to add it to both sides. Right? Right, so they all have the same sign here. That's kind of ugly now. Okay. Alright, so now all we need to do is just kind of divide. We notice there's a G common in both terms here, so I'll factor that out. So we get A equals G times a really ugly fraction. So we have the capital M minus mu K2 M1 plus M2. That's the numerator. We divide by that whole sum of masses on the other side. Like so. And so that is the answer. Right? It's ugly. There's a lot going on there, but it's really just about careful algebra. That's all you need. And then some sort of careful substitutions. Okay, so finally, part D. Now we're making another change. We're saying that the hanging block descends, and block 1 and block 2 don't move together anymore. That complicates things, right? Now we can't make that combination that to simplify the problem. We have to treat each block individually. So we need to figure out the acceleration of each block individually rather than the combined 1 and 2 blocks. And that means we really have to redo the free body diagrams completely, which seems like overkill. Right? You notice that even though we did free body diagrams in part A, I'm redoing them a little bit for part C and D. And that's because when the accelerations change, the physics changes. And so the free body diagrams you drew in part A don't always apply to the problems. They give you a bit of a guide on what you're doing, but you really should redo it from scratch so you don't make silly mistakes or mistakes that could be prevented. So D part 1 deals with block 1, so I'm going to draw block 1 and figure out all the forces on block 1. So we know we have normal force, we know we have weight. And so now, block 1 is moving to the right. We need a horizontal force to make it move to the right. And remember in part A, we said the frictional force was 0, but that was when the blocks were at rest. Now it's accelerating. We need that frictional force to make it move. And it has to be to the right, because otherwise, why would the block move to the right? And you should have an intuition that that's how the block has to move. So, this problem is actually deceptively simple, because all we care about is the acceleration of block 1, and block 1 is very simple for its forces. Why does it move? We know it's slipping on block 2, so this is kinetic friction, right? Because it's moving relative to block 2. And we know how to calculate kinetic friction. And we know why it moves, because of the kinetic friction. So, using F equals ma, we get F1 equals m1a. That's it, right? Why does it move? Kinetic friction. Well, mu k1 times n1, which is m1g, equals m1a, right? All I've done is substitute in the definition of the friction force. We can cancel the m1s, and we find that a is just very simple, mu k1g. And that's it. It doesn't matter what block 2 is doing. It doesn't matter what the hanging mass is doing, because the only interaction that block 1 has with the rest of the system is through that kinetic friction. And that's the only thing that gives it an acceleration. So it's a much simpler problem than it first looks. Unfortunately, part 2 of D is not quite that simple. And so we have to go and draw a free body diagram for block 2, really from scratch. So I'm going to do that. So, block 2, I think I'll do it in blue. Block 2, when we're in this complicated situation where block 2 is moving and block 1 is slipping on top of it, a lot of the stuff is the same, right? There's still a tension. There's still normal force 2 and normal force 1 and the weight of block 2, right? None of that changes. There's still friction between the surface and block 2. But the important new force to consider, and the easily forgotten one, is what about this, right? Remember, that's the force that block 2 exerts on block 1. So Newton's third law tells us that there's an equal and opposite force of block 1 on block 2. Right? That's what this arrow is right there. That's a third law pair. And it's very, very, very easy to forget that force. So if I'm going to now do an equation of motion for this, right, it's going to be moving to the right, so the tension is still the positive. But now we have 2 friction forces that we have to subtract from 2 different surfaces of contact. And now, since this free body diagram is only for block 2, our mass that's accelerating is only block 2's mass, right? Not block 1 and block 2 anymore. So now we're in a situation that's very similar to what we did before, right? The hanging mass has not really changed, right? The hanging mass is still tension up, capital mg down, and its free body, or its equation of motion that comes from that is going to be the same, capital Mg minus T equals capital Ma. This one I'm going to solve just kind of not backwards, but I'm going to substitute the other way because this equation is kind of ugly. So we get T minus, or the tension equals mg, or sorry, I'm going to do it the other way around, ma minus mg, right? And then this will come over into there, and I'll start working in black. So ma minus mg, that's the tension. Now, Fk1, the frictional force from block 1 on block 2, we already know that. We kind of calculated it before. Mu k1 m1g. Friction force number 2 is based on normal force number 2. And that part actually hasn't changed from the early part of the problem because our vertical acceleration has never changed. It's always 0. So n2 is the same as it always was. So this is mu k2 n2, which is m1 plus m2g. Right? That's the same as it was way back, right? Way back here. Right? That hasn't changed because our vertical acceleration has not changed. And that all equals m2a. Okay. So now, if you got to this point, again, it's just algebra. You have to be a little careful, but it's not too hard. However, you need to be careful with signs, which is I see I've actually made a mistake. So I'm going to erase. I made a slight error in here. I flipped my sign. This is mg minus ma, not the other way around. So let me clean that up. mg minus ma minus. There. Okay, so we put everything with a on one side and factor it out. So we have a times m plus m2 equals, we notice our three terms that are left over all have a g in them, so we'll factor that out. And we have a capital M minus mu k1 m1 minus mu k2 m1 plus m2. And now we can just divide by the m plus m2 and we're left with our answer. Once again, kind of an ugly fraction. Right, so we copy all this over. And that's it, right? That thing. So again, this problem is a really good test of how comfortable you are with carefully paying attention to interactions in systems, because it's very, very easy to try to rush through it. You notice how this took me, obviously, substantially longer than the 15 minutes allotted. That's because I was explaining everything in detail. There are definitely some parts where I feel you can go much faster through, especially part A, but it is important to work very carefully, because this problem is one where if you make a mistake in part A or draw too many conclusions from incorrect assumptions, you can make a lot of mistakes very quickly. So it's very tricky as a whole, but as long as you work through it slowly, you can get it right.